Thanks very much, Craig. Good afternoon, everybody. I'm going to be giving 3 short talks in this short period of time. The first one involves the Trek Treetop Survey area that Wayne and Dave were talking about this morning. So some of the slides that I have here will be able to go through quite quickly. This is where it's located. Now, why bother with treetop sampling? Well, okay, I'll be back in about an hour and a half, okay? Let's snooze that one. First survey I ever did of this sort was at the QR in just to the east of Quesnel in 1988. Didn't have GPS at that time. We just had to sort of measure the distance between a lake and where we were, and then time the samples that the helicopter would time the time that the helicopter was flying, and then calculate back. Anyway, it came out rather nicely with some extraordinarily high concentrations of gold in the Douglas fir treetops. These are concentrations in ash, up to 738 ppb, and they all were, the high values were all concentrated north of this main zone here, and we didn't see any sort of signature from the west zone. Now, with the Trek survey, treetops were collected the same way, and the first samples that analysed were the twigs, and secondly, the needles. And as you see, quite a lot of information can come out of this. We did another survey back in 2006 and dug the archived needles out of the collection and got those analysed just on the dry tissue. And basically, we came out with the same sort of pattern. It's a little bit different. I think we picked different percentile levels there, and we actually were able to see the synclinal nature of this west zone at that time. An important fact out of this is that if you've got samples and you keep them and you want to go back 20 years later, you can do it. They've not degraded at all as long as they don't get wet. Well, this is, anyway, the reason why we went ahead with the treetop sampling. There was another big survey, a bit bigger than yours, I think, Wayne and Dave. There was 700 square kilometres in the Monarchies where we collected Douglas fir treetops and again compared twigs and the needles, and there's out of that there was no known mineralization whatsoever down in this area. There was a bit up here, not where these anomalies are. Thallium came out unusually high. I'd seen high thallium values in trees from New Brunswick, and so followed up on this, and this is ongoing, but so far we found up to 19% zinc. So it works. So going back to the Trek area, I don't have to say much about the geology here. This is the black hole that we've seen in the earlier slides today. This area is all the Chilcotin basalts with variable cover of quaternary. You've got the Naglico and I don't know my geology well enough, sorry. And the Utsa Lake group up in this area. There's the 3 T's that you can just about make out there. That, I believe, is the only known mineralization within this area. So the area sampled went as far north as the 3 T's, and as you'll see in a minute, down towards the bottom of that area. And there was really no other way that anybody could think of doing a geochemical survey in there, that area. So my involvement with it was just to get the program set up based on my experience in other areas, and then really just leave it to Dave and to Wayne to look after pretty well everything else from there on. As I said, the survey area is underlain mostly by Utsa Lake group and Chilcotin group volcanics. The prospects are mostly to the north, but there's the potential for gold, silver, zinc, lead, and copper mineralization in the region. We've heard about the Blackwater Davidson area today, and the 3 T's I mentioned is silver, lead, zinc, and gold. The survey involved White spruce tops, 421 trees were collected. I think you've got 399, Dave, and that must include the duplicates there. 1,000 square kilometres, all covered in 6 days. The trees were healthy, 20 to 25 metres tall, all 80 to 100 years old, and the bits that we collected were where the spires were emergent out of the canopy of the forest. At each sample station, about 1 kilogram of sample was collected. Back on the ground, these were trimmed to just the 5 to 7 year old growth, because there's seasonal variation in chemistry. 500 grams were sent to Bureau Veritas for drying and separation of needles and twigs. Twigs were milled to 1 millimeter, needles reduced to ash, and both tissue sets were analysed by ICP-MS for 53 elements. That's the aerial view from the helicopter. Trees, all trees, some burnt, and there were some bogs, but that really didn't affect the survey. And this was the procedure where somebody in a nice harness leans out, snips off the side branches of the tree, as you can see there, hauls it back in, hands it to the person next to him, and the GPS is being punched at that point to record the spot. And all the rest of the bits I've got on the left, I've just went over just now, but this is what the final sample looked like before drying and separation of the tissues. Now, I've just got a couple of examples that I plotted up showing the distribution of a few elements in the spruce needle ash, and these actually are values that have been leveled to a dry weight. What can we see out of this? Well, there's a general concentration of molybdenum off to the west, which is quite intriguing. And clearly, well, to my knowledge, nobody's followed up on this yet, but does that mean that you've got some mineralization beneath that cover? At least it sort of narrowed down the areas for looking, so there would be that. And then there's this linear trend of arsenic anomalies, which looks a bit suspicious, but you heard all about the really rigorous QA/QC that was being done on these data sets that Wayne and Dave have collected. And so they've passed all of the QA/QC. This is the general direction of glacial movement from the west to the east. So there is a clear trend there which might be worth thinking about. Silver, like the molybdenum, comes out really quite nicely in this western area. Copper, mostly concentrated in the west to northwest bit, so the element assemblages are coming together nicely. I would just point to this one, because this area comes out as being anomalous in several elements, so that might be worth considering. Zinc, there again down in this area, and cesium is an element I've found to be associated with, in the trees in particular, with several styles of mineralization, in particular gold. 3Ts is up there, and it's spatially associated, actually, rather than directly above gold mineralization. So another geochemical anomaly up there. Gold itself, now this looks quite suspicious, this linear trend of samples. It looks as if it's an analytical artifact, but as I said, the QA/QC was done very thoroughly on it, but as thoroughly as it was done, I would be a bit suspicious of this. You don't usually see a really nice trend like this without some sort of analytical artifact, put it that way. But we got this same area coming out here, and the same for cadmium. That's all I'm going to say with regard to the treetop survey, but maybe the way for the future is to develop one of these things, have a little arm come down and go out and go cut off the top of the tree, drop it in the bag. It's a wonderful job for an engineer to deal with. And that would be a quick way of getting around difficult country. And it saves all of the questions by the health and safety people in the big companies who don't like people leaning out of helicopters for some reason. Now, the other aspects I'm going to deal with are plant exudates. I worked with Dave Heberlein on this, and really, Dave and myself are totally responsible for these. Bill McFarlane kindly joined in with the analytical aspects the first time we had a go at this, and he was with Bureau Veritas at the time. And we were looking at the Wood Jam project, which is a blind copper porphyry. The objectives at this stage were just proof of concept. Investigate the metal contents of a variety of plant exudates, tissues, and organic soils over mineralized and background sites. Determine whether metal concentrations of exudates identify the position of blind mineralization, and develop an inexpensive geochemical sampling approach for exploration in covered areas of BC. A lot of information on here, but basically, if you've got a mineralized zone here, which is steadily degrading and metals are getting into the subsurface, perhaps by bacterial action, into the water table, get taken up by the trees and the roots, and over on the left there, these are the mycorrhizae which grow on the roots. They're really like little tiny fungal filaments they are, and that is about a 2-inch tall pea plant, and that's the whole mass of mycorrhizae around it. So you get an enormous length, many tens of kilometers of roots, rootlets, mycorrhizae from a single tree. The metals get drawn up into the plant. Sap leaks through wounds in the bark. The metals continue up the tree. Some get deposited in the tree. Then the trees transpire, and some metals go out with the solutions that transpire. The metals that get incorporated in the tree tend to go to the extremities, particularly the outer bark and within the twigs. And here you can see an example of a scanning electron micrograph of gold in the outer bark. It's a crystalline phase of gold which is developed in the outer bark of a mountain hemlock in that case. So that's the theory and what we believe happens. So exudates are any material that's transpired, excreted, secreted, or otherwise leaks out of a plant. And I'll go into these differences in a minute. Part of our experimentation. Looking at sap first, the literature tells us that there are some plants that can hyperaccumulate metals, and they are. This Sève Bleue from New Caledonia has been found to have more than 25% nickel in the dry sap. Its subsequent tests have found it to be a nickel citrate, which has given it this blue color. Much less, but still an awful lot of nickel in the bark, and less still in the wood. The woody parts are not really nearly as useful as the extremities of the plant. So our project location for the wood jam, we looked at 2 areas. I'm just going to give you a few examples from a traverse across the Deerhorn study area, and particularly, these were all of our sample sites for a variety of media. We didn't get all media at all sample stations. It really wasn't warranted for our objectives. So you've got a situation where you again got Chilcotin basalts, and basically the traverse is starting in monzonite, going across into through the green bit into andesite, and that is the extent of the traverse that we'll be looking at. This is the 0.2 gram per ton gold equivalent cutoff. This is the list of the media that were collected, and we did comparisons of all of these, and all of this information was published. But I'm now just going to concentrate on these 3. We just tied plastic bags over the end of a twig, left them out in the sunshine for the day, and at the end of the day, you have an accumulation of water that has transpired through the plant. A big tree can transpire many gallons of water during a single hot summer's day. So nothing very complex about it, and as just a couple of examples, we only had 10 of these sites, but you can just see by looking at the median values in the background sites, 3 ppb copper, we're in the ppb levels, 3 times as much at the anomalous sites. Sulphur, Much the same, really, getting on for 4 times as much at the anomalous sites, but the higher sulphur concentrations over the mineralization. Thallium, one of my favorite elements nowadays. I like thallium, rhenium, and others. But thallium can be a very useful pathfinder. We were testing, trying to figure out the best way to collect the sample the first year, and found that this idea of scraping it was not very efficient. You get a lot of bark particles in there, then you have to spend ages picking it out. But we did that for that survey, and I'll show you what we did in the next survey shortly. And here are the results for the sap. Rather more samples that we collected, arsenic was giving a good signature right the way across the zone of known mineralization. Copper only marginal to it. Tungsten, that's the other one I like, was good through there. Mercury really good. I like that now as well at the moment. So we were getting good signature in the sap over the deeply buried mineralization. We did try particulate sample because you may know that Tony Barringer had the air trace system where he flew over the forest and sucked up the particulates coming off the vegetation in desert areas, and was able to, I think he got an ICP-ES on board, and he was able to analyze them right away and be able to see what the metal variation was. So we thought we would try that, because Tony's method was one step better than the Pete Sainsbury used to work for the USGS, where he had his own Piper Cub, and he just would lean out as he was flying by and whip the tops off the trees, and a clay ball on a rope, he would slam it into the ground and get a sample of rock. Anyway, Tony was 1 degree of sophistication better, so we thought we'd try that. And here you're looking at an SEM of a spruce twig, and you can see that the cuticle and the waxes are spalling off. So that's happening all the time. However, we got nothing. We sucked and sucked and sucked. There's Thomas Bissek trying to get some particulates, and nothing came off at all. So we abandoned that, and I have nothing more to say about particulate sampling. We collected alder leaves, and we collected spruce needles, and we put them into separate bottles, and they were leached with chloroform, and again to try to strip off the waxes that hadn't already got blown away. We had a problem with the leaf coatings because we didn't realize that you put leaves into a plastic bottle and they go all rotten very quickly. So there's some sample degradation, but even so, we've got a signature for zinc. The needles that much more stable. We're getting a good signal of sulphur and moly through there. So the initial results were encouraging. The signal from blind mineralization appeared to be present in some exudate media, particularly the transpired fluids and saps. The very low detection limits required to see the patterns may be beyond the capabilities of commercial labs. That's what we said at the time of the study, 2012, 2013. So the next stage was to try to get something that would be commercially viable. If you're going to use it in exploration, you don't need to, you can't send everything to a research lab. It was Queen's QFIR that had done the analytical work for us for the first lot. So northern part of the Trek area, Endako, where there's plenty of molybdenum, as I'm sure everybody knows. Basically, you've got intrusive phases of batholith, Upper Triassic to Cretaceous Endako batholith, various different phases, surrounded by volcanic and sedimentary rocks ranging in age from Jurassic to Oligocene. And there you see the map of the Surficial Geology cover. Lots of green, which means it's till blanket and till veneer, with patches of all of these other things through there. But most of our sample sites were over the till. We found that the best way to collect the sample was with a simple pocket knife and just flick little bits of hardened sap off into a pan and pour them into vials. We did have comparisons with a number of media. We had AH horizon soils, we had spruce bark, we got a previous survey of pine bark, and we had pH, some soils were collected for pH measurements. I'm only just going to say a little bit more about the sap sampling. There's quite a lot of variations in spruce sap, and quite surprisingly, we found that every tree that we went to actually did have some sap exuding. That spruce, if you look for the pines, it's not so easy to find. It's often just that crusty, tiny little white particles that sit on the surface. That's it. That's all you're going to get. So you'd have a problem doing that, but if you've got a spruce forest, this is a possibility to go ahead with this. We did look at the different chemistries of the different colors of sap. There was blue sap, and I immediately thought, oh, wonderful, we've got nickel, but no, nothing there. It's just the same composition, and the occasional bug had crept in and didn't make it too far. The method development, as I said, the first lot was done at QFIR in 2012, but then ACT Labs took over with our Endako survey, and they experimented with various organic solvents, acids, and varying dilutions, and they came up with a method to clean the sap by dissolving in methanol, pass it through a 0.45 micron filter and re-solidify, digest it in nitric and perchloric acid, and then analyze just with an adjuvant 7700 or 7900 ICP-MS instrument. After filtering, you could see that we've now got rid of any dust contaminants that there might be on there and any little remnant particles of bark. And that's the clean sap that was solidified, dissolved, and then analyzed. Just to look at some of these impurities. Basically, the impurities are these calcium oxalate crystals. And a couple of plots of the data. Here's moly in sap. So we've got a very nice signature of molybdenum all throughout the whole of the Endako area, and over in one or two other spots a bit. There you see rhenium and bismuth. Rhenium, of course, is often associated with moly. Bismuth has got a good signature in there. And just four more elements: lanthanum, tungsten, uranium, and thorium. So in conclusion, the initial results from WoodJam were encouraging, especially from saps, but the microwave digestion in concentrated nitric with a high-resolution ICP-MS finish would require really a research lab, and therefore it would be expensive. Now, our experimentation on the Endako samples, thanks to ACT Labs, concluded that the optimal method was dissolution in methanol, filtration, digestion in nitric perchloric, and finished with just a regular ICP-MS. Most labs have got an adjuvant 7700 or the equivalent nowadays. And with the very low detection limits, we could see the patterns and that they were within the capabilities of the commercial labs. There were strong signatures in saps collected soon after they had exuded from the trees, not the result of a long period during which surface contaminants could have accumulated. Sample preparation and digestion procedure designed to filter out any mineral dust contamination that may be adhered to or included in the sap. Molybdenum gave a robust response in all media: sap, AH, pine bark. Strong signature of rare earths in the sap. Uranium and thorium were strongest in the sap. Tungsten, moderate signature in the sap. And there you see the list of elements that all had a strong signature, and it's the suite of elements that defines the Endako mineralization. Thank you.